Welcome to our discussion on combining functions and dealing with composite functions. As always, you can fast forward to the section that you want to look at. You'll see this card come up every time we talk about a new topic. First, we'll discuss some of the definitions. When we talk about a sum, a difference, a product, or a quotient, it's just what you're normally used to. Add things up for a sum, right? Take differences, products means multiply, quotient means division. So don't get caught up in the vocabulary. It's really nothing different than you've already seen. Now the syntax here might seem a little confusing, but it's actually quite basic. The thing to remember is that if you're combining two functions, right, this just says take the f function and the g function, add them together, and then both of those functions are in terms of x. This is just a fancy way of writing take the f function and add it to the g function, right? So this is just a shortcut way of writing take the difference of the two. This is the shortcut way of writing multiply, and this is the shortcut way of saying divide. But of course here we have to say that the bottom function can't equal 0 because we can never divide by 0. So now that we understand what the syntax means, we can now answer questions when they ask us to perform these things, because this first piece here, A, is simply asking us to take the f function evaluated at 4 and then subtract the g function evaluated at 4. And then this b part is just saying f of 3 over g of 3. And the same for all the rest. But these last four, you'll notice they're no longer evaluating at a number. They're asking us to just evaluate it at x. And that's going to be a little different, just slightly different, but not too big of a problem. So let's look at the first two, because they're the easiest ones. Because if we know that f minus g of 4 is really just the same thing as f of 4 minus g of 4, all we have to do is do both of those operations and then subtract. F of 4 is simply 4 squared minus 6 times 4 plus 8, right, which is 16 minus 24 plus 8, which is 0. And then g of 4 is just 4 minus 2, or 2. So f of 4 minus g of 4 is simply 0 minus 2, or negative 2. It's just that simple. Don't overthink it. Okay? Here it is written out all nice and pretty for you. And then we did the same thing with f of 3 and g of 3. We evaluate the function, the f function, at 3. It's the green bit. And then we come back and we do the g function evaluated at 3. And then f over g of 3 is just f of 3 over g of 3, just the minus 1 over the 1. And then there is your answer of negative 1. Simple, simple, easy. Here's where it gets a little trickier, because when we have to do these functions in what we're going to call the general case, right? We're no longer doing a specific case of 4 or 3. We're now doing the general case of just x. And when we do the general case, we can no longer just plug in a number, get an actual answer, right? Get a number, and then add it to another number, or subtract it, or multiply it, or divide it, do any of those 4 simple operations. We now have to deal with the function in general. So when they ask for f plus g of x, we have to actually take the f function, and the f function is all of that, right? That's our f function. And then we just have to add it to the g function, so we have to add all that stuff. And just like we did a long time ago with adding and subtracting polynomials, you just add like terms. Right? There's only one x squared, there's no over here, so we combine like terms of the x's. We've got negative 6 plus one of them, that gives me negative 5, and then 8 plus a negative 2 gives me 6, and there is my ultimate answer. Same thing goes with subtraction. You start with the f function, subtract the g function from it, being careful to realize that you're distributing, right? You're subtracting x and you're subtracting a -2. So -6 minus x, that's why you get -7, but then you have 8 minus a -2 becomes 8 plus 2, and that's why you have plus 10. So adding and subtracting, pretty easy. Multiplying is not too bad either. It's just multiplying polynomials, which we learned how to do a long time ago. You can use just regular multiplication. It's kind of like foiling, but remember, you want to be more systematic. The best thing to do is just start with the first term and multiply through. So x squared times x gives you that, right? And then times -2 gives you that piece. Then you move on and you do this one. -6 times x gives you -6x squared, right? And then times -2 gives you positive, right? Because negative times negative. Then you move on to the 8, and that gives you this piece and that piece. You combine like terms, and there's your final answer. Division, of course, is the ugliest of them all because dividing polynomials can be tedious. It's not difficult, it's just tedious, and hopefully you'll remember that when we want to divide polynomials, the first thing we want to do is try factoring the top, which we did here. Then those will cancel, and there's our answer. If it didn't factor nicely, then we could do long division, and we could get an answer with the remainder. There's all sorts of things we could do. Usually, if you end up having a remainder, it's cleaner just to leave it as a big old fraction rather than having a polynomial plus a remainder. But it just depends on the applications. Okay, so add, subtract, multiply, divide just brings us back to adding, subtracting, multiplying, and dividing polynomials, because now those polynomials are just being called functions. So there's no real difference in what we're doing mathematically. Okay, now we're going to talk about how to form composite functions. This is different, right? But before we knew how to add, subtract, multiply, and divide. Now we have to figure out how to do a composition of two functions. A composition, f of g, means you're taking the f function and putting the g function into it. So those are the two different ways of writing the same thing. F of g kind of looks like fog, and then on the right hand side, f of g of x. Here's a nice picture for you. F of g of x means first you take x, put it into the g function, get an answer, take that answer, put it into the f function, and get your final answer. And the f of g arrow is just kind of showing how you can do it in one step. Now this might seem kind of counterintuitive. Why are we doing the g function first when it's f of g of x? Well, remember your order of operations. First you do things inside the parentheses. So first you do inside that first set of parentheses, which means you have to do the g function first. Then you move out and do the f function. Right, so you're working from the inside out with this type of notation. Here's a simple example. Now before we get into all of this down here, remember that when you're talking about a function, your variable becomes like a little bucket that you can pour anything into it. So if I asked you to do f of p, what would the answer be? And hopefully you're all saying it's just p cubed. Okay. What about f of 3? And you go, well, that's easy. That's just 3 cubed. And I say, okay. What about f of x plus h? Remember doing the part of the difference quotient? And you'd go, okay, well that's also easy because I just take the x plus h and put it in for the x, and it's going to be that thing cubed. Now I would cube it all out and I'd get this big, huge, ugly looking polynomial. Okay, so what is f of x plus 1 going to look like? And you go, well again, that's easy. That's just x plus 1 cubed. Well, guess what you just did? This is f of g of x, right? Because we just took the g of x function, x plus 1, and plugged it into the f function. That's what we're doing when we're doing f of g of something. Now the easier ones are when they want you to do f of g of a number, because that's simple. That means we're just taking f of g of 1, and g of 1 is simply putting 1 into the g function, right? G of 1 just equals 1 plus 1, which equals 2. So this question is really just asking f of 2, and f of 2 is just 2 cubed, which is 8. Done. Simple. If we want to do g of f of 1, right? Different, right? First we did f of g, now we're doing g of f. That means we're doing the f function first and then taking the g of it, right? This lovely stuff right there. And f of 1 just equals 1 cubed, which equals 1. So this is really just g of 1, which is 1 plus 1, which is 2. Now you'll notice the answers are different. We got 8 when we did f of g. We got 2 when we got g of f. So what does that tell you about f of g and g of f? It tells you they're not the same. They can sometimes equal each other, and if they do, then those two functions f and g have a special relationship. We'll talk about that later. But for now, just realize that f of g of x does not equal g of f of x as a general rule, right? It can, but it's not an identity, right? It's not like it always happens. So you can't assume that. F of g and g of f are not going to be the same thing most of the time. Sometimes they are, but most of the time they aren't. Now f of f just means take f of the f function. So first you plug -1 into the f function, you cube it, which gets you -1. Now you take f of -1, so you cube it, and you get -1 again. That's just a silly example, right? If we did something different, like f of how about 2, then you get f of 2, and f of 2 is 8. So this is really f of 8. And then the answer would be 8 cubed, which is really super big, a lot bigger than 2, right? So you don't end up getting that kind of same answer that you do with the f of -1. Composite functions, when we want to actually find the general form of a composite function. Remember we talked about the difference between general and specific. These are specific examples where we're compositing at a specific number. G of f of 1, f of -1, right? F of g of 1, etc., etc. Now we want to find the actual general form of the composite function. What does it mean to just have f of g of x, right, in a general form? Because if we can find out what this is, then if they ask us to do f of g of 2, we can just plug that answer into the new function we get. And then if they come back and ask us to do f of g of 3, we can plug that into the new function. It's going to save us time anytime we have to find f of g of more than one number. That's really the only reason why we would want to do it. So let's take a look at a simple example. F of g of x. Again, it's f of the g function. So you're taking f of the entire g function. So you're taking that entire function and plugging it in for all of your x's in the f function. So 2 times it, right, plus 1. Distribute, put everything together, and there's your final answer. Nice and simple. So now when they ask for f of g of 2, you could, of course, just plug 2 into the g function, which will give you 4 minus 3, which is 1, and then plug 1 into this function, which will give you 2 plus 1, which is 3. Or you could take the 2 and plug it in here, and 2 times 2 is 4, right? 4 times 2 is 8. 8 minus 5 is also 3. It should work both ways. This is only helpful, like I said, if we also need to come back and do f of g of 5, right? F of g of -2. Instead of having to take these numbers, plug it in here first, then plug it in there, right? Take this one, plug it in there first, and we can just plug them into this function each time, and it saves us a little time and energy. And plus, it's also nice to know what the composite functions look like, because now we know from our family of functions, what is this graph as? What does it look like? It's a parabola. It's facing up because this is a positive number, right? It's been shifted down by -5. Right? The 2 makes it stretch, so we know kind of where it is, what it looks like, and those types of things. Here's our other example of g of f of x. So we're kind of going in the other direction. Instead of f of g, we're doing g of f. So now we're taking the f function and putting it into the g function, which is going to be a little trickier because now we have to square a function. 2x plus 1 has to be quantity squared. So that's when you want to FOIL that out, combine like terms, and then subtract the 3 from it, and then that would be your final answer there. The f of f function, so you just take the f function and pour it back into itself. So 2 times it, right, and then plus 1. And that's doing composite functions, guys. That's the whole idea, is just always remember to think of your variable as an empty box or an empty bucket that you're going to put something in. So instead of x squared plus 3, I like to tell my students, think of it this way. It's some box squared minus 3. And so now when you have to do g of f of x, you know that you're putting f of x in each box, right? Or more specifically, you're putting 2x plus 1 in there. And it just helps you realize that that whole quantity is being squared. You're not just squaring the 2, or you're not just squaring the 2x, right? You're squaring 2x plus 1 as a quantity. Because these things will get more complicated eventually, where you'll have, 3x squared plus 2x plus 3. That's going to be your g function, and your f function is going to be, let's say, x minus 5. And now they want g of f. And now you got to plug this thing in for every, sorry, that should be 2x, for every x. And it's not difficult, it just has a lot of places where you can make a mistake. So take it slow, be systematic, give yourself the little boxes, right, and put everything in the boxes so that you can remember to square the appropriate things, multiply the whole thing by 3, etc., and not make any silly mistakes. Finding the domain of a composite function is really no different than finding the domain of any other function. The rules still apply, right? All polynomial functions have domains of everything. The only problems we have with domains is dividing by 0. So anytime we have a function with something in the bottom of a fraction that could equal 0, that's where we have to worry. Or square roots, right? Even square roots, where this is an even, a 2, a 4, a 6, an 8, we can't have negatives in that. So anytime our composite functions have those same two quirks, then we have to worry about the domains, and if they don't, then their domain is everything, just like any other normal function. So the example here is g of f of x, which ends up giving you 1 over x plus 1, and so obviously the problem is we can't let x equal negative 1. Decompose a function. This is a really good skill to have for when you move on to calculus, because it will help a lot with integration by parts and other techniques. You need to be able to look at a function and see how that function is actually a composite of two other functions. And what you're always looking for is you're looking for a composite of one of our general functions with something else. So remember, our general functions are things like x squared, right? X cubed, 1 over x, square root of x, right? Just our simple things. Absolute value of x, all these types of things. So when you look at 1 over x plus 1, hopefully you can see that that is 1 over f of x, right? Where f of x equals x plus 1, and then our g function is just the simple 1 over x, it's x plus 1, and so this ends up being g of f of x, right? Because the g function says take 1 and divide it by something. And if we do the g function evaluated f of x, then that says, okay, take 1 and divide it by f of x, where f of x is this piece. So we now took this thing and we've written it as two separate functions. Let's look at another example. So there is our 1 over a square root of some junk. And they want you to define g of x as any expression in the defining equation for h. And they picked it for you. So if g of x is going to be that, well, these two things are equal. So by substitution, that just means h of x, right, equals 1 over the square root of g of x by substitution, right? So what's the general form of, the h function? The h function is really just 1 over the square root of something, whatever it happens to be. So we can now write this as h of g of x, where h equals 1 over the square root of x, and then g equals what we have. Now they're probably going to give us two new names instead of calling it h. Right? They're going to call it f. So it's now f of g of x, but you get the idea, right? You're just simplifying it and pulling them apart. That's what it means by decomposing or decomposition. You're pulling them apart. You're seeing the two pieces that make up that composite function. Here's another example. We can calculate the area of an oil spill from a tanker. So if oil is spilled, we know that the area of the oil spill is going to be a perfect circle. I mean, it's not going to be in real life, but if there wasn't any friction and waves and things like that, then oil would go out in a perfect circle. The radius of this oil slick increases at a rate of 2 miles per hour. They want you to express the area of the oil slick as a function of time, and then calculate the area covered by the oil slick in 6 hours. So the radius is a function of time. When they say it's increasing at 2 miles per hour, that means the radius is this function g of t, which is 2 times t, or t is time. So for every hour, the radius is 2 times that t. The area ends up being a composite function of that, because area is pi r squared, right? And in this case, it's f of g of t, so it's f of 2t, so it's pi r squared, but it's pi of 2t squared, which gives you the 4 pi t squared. So there's our function that represents area of the oil spill in terms of time instead of just in terms of its radius. So we found part A. Part B was they want to know how big the oil spill is after 6, what was this, in hours? Hours. After 6 hours. So you plug in the 6, you get 144 pi, and if you plug that into a calculator to figure out what pi is, it's roughly 452 square miles, or a lot. Okay, applying composite functions to practical problems. Well, we already saw that in the first example, or the previous example with the circles. Here's another similar example. If a car dealer offers an 8% discount off of the manufacturer's suggested retail price for any new car on the lot, at the same time the manufacturer also offers $4,000 rebate for each purchase of a car, they want us to write some function r that represents the price after the rebate. I would have called it p of x, but they're calling it r of x because of rebate. They want us to also write some other function d of x that represents the price after the dealer's discount. So now I can kind of see where they're going with this. R for rebate, D for discount. Then they want to write the function R of D of x and D of R of x and figure out what those represent and then calculate them each. Very simply, the rebate, right, was $4,000 off. So whatever the price of the car was, you just subtract 4,000 from it and there's your R of x. That's your new price. The dealer's discount, however, was 8% of the price off, or 0.08% taken away. So you start with your price of x, you subtract the 0.08x from it, and you're left with 0.92x. And if you look at that, isn't 0.92x 92%? Well, if you take 8% away from 100, how much is left? 92%. So that's what an 8% discount looks like, right? It's 92% left over. So those are your two simple R and D functions. Now R of D. So R of D says take the D function and put it into the R function. The D function was the dealer's discount, right, which was the 92%. Then we're going to take the R of that, and the R function, if you don't remember, the R function was simply x minus 4,000. So that's how you get this. And this represents the price when the dealer's discount right, is applied first. So first we discount the car by 8%, then give you a rebate. This formula here, however, we're doing D of R. So we're doing the dealer's discount on the reduced price, right? The car minus 4,000. So now we're taking 8% off that reduced price. So there's my 0.92 minus 3680. That's the price when the manufacturer's rebate is applied first. So first you take the $4,000 off, then you take 8% off. Well, which of the two would be the better deal, right? If you were trying to buy this car, which one would cost less to you? And hopefully you can see very clearly that this is the better deal, because whatever the price of the car is, you're still getting 0.92 of it, right? You're still paying 92% of that price, that X. But in the first case, you also take $4,000 off, whereas down here you only take $36.80 off. And if you look at the difference between those two, right, it costs $320 more if you apply the rebate first and then the discount. Kind of good to know if you go in to buy a car and they're trying to mess with you and, get some extra money out of you. That's it.